Do some. Morning. Can you take your seats, please? We are going to start in 1 minute, please. Can you take your seats? Please, we are starting. Please. Okay, so hello, good morning, everyone. Welcome to Granada. So it's really, a pleasure for all of us to have you here. This is today a very, very special day. But before we start with the science program, I'd like to make just a short announcement. It's what we would expect when we have a gather of many people traveling around the world. That yesterday we were reported 2 people that gave positive in COVID. Nothing to panic, it's exactly what we would expect. These 2 persons are perfectly healthy. They have been informed all the people that were in close contact yesterday, and they are in contact with health authorities in Granada. So everything is absolutely normal and fine, what you would expect in these cases. In any case, for those of you that would like to take any extra tests, at the desk and at the reception, we have 4 free tests. So anyone, if you feel like you have some mild symptoms, please go there. There is a free test. If they run out, we will buy more. So just be mindful of that, and there is nothing to worry. But we want to be completely open about this, and so people will feel comfortable and secure and everything. Of course, if you need any information or you do feel that you are not feeling well, please do contact any person from the lab. Okay. So besides this, then again, this is a really special day for us. I mean, for the EHT organization and the ngEHT organization. This is the first day for the EHT in which we host an open session, and we are thrilled to share the results with the broader community. And it's also this very special day because we are joining together the EHT and the ngEHT. So this is really, as I said, very special for us. And again, I have to click here to get this going on. Okay, yes. So today is really an excellent opportunity for the first time to join all efforts and then to bring these 2 communities to revolutionize our view of horizon scale physics through the first movies of black hole accretion and dynamics, to establish the connection between these supermassive black holes and the production of a relativistic jet, and to discover a wealth of new black holes and explosive transients to explore. And we can do all this together, joining the efforts of the EHT and ngEHT. And this is not working. Okay. So in today's program, we will start with the latest EHT results on SciJ. And so we are going to share this for the first time with the broader community. And we will also review a decade of discovery in black hole science. And we have the honor, the opportunity to have 4 speakers that we will tell us about this. So we have Frank Eisenhower, who is going to talk about the richness and power of near-infrared interferometry. Sfera Markov, who is going to talk about multi-wavelength observations of SciJ and low luminosity AGN. Priya Natarajan, who is going to give us a talk about black holes and the cosmic context. And Jim Moran, we are honored, who has not read the Bible of a VLBI. So we are honored to have Jim here. He's going to give us a VLBI historical perspective of VLBI. And besides, then after this, we will have a special session in which we will dream big and think about amazing possibilities that the next decade will bring for the next generation studies of black hole imaging. And we will end up at the end of the day with a session that will be a panel discussion with the 4 invited speakers and all the audience, where we can discuss the amazing things we can do with the EHT and ngEHT in the next decade. And also remind you that the ngEHT meeting is going to last until Saturday. Okay, and this is for the ngEHT is really a very special occasion today, because we have had previous meetings. We had a meeting in February 2021. We were discussing that was the first online meeting discussing the next generation EHT. That was followed by another meeting that we hosted in November last year, where we were discussing how to go from the vision to an instrument. And today is really the special day, because it's the first time we meet in person. And this will be an excellent opportunity for bringing the whole community, bring together experts in black hole astrophysics and also VLBI technology. We would like to have a wide range of talks and discussions to sharpen the ngEHT scientific vision and to make crucial architecture designs. We will have a joint ongoing scientific and technical efforts and discuss the collaboration. We need to put everything to all the international collaboration together to assemble this new instrument capable of producing this visionary science about black holes for the next decade. And I would like also to announce that we are now working on white papers for the ngEHT. We have different working groups, as we will see in the talks today by Shep and Michael, and we are drafting these white papers that are going to be published in a special issue of the journal Galaxies, and we expect that this will be a clear description of the science and the vision that we have for the next generation EHT. Before getting into the meeting, I'd like to give a special thanks to the Science Organizing Committee for the ngEHT, Every Broderick, Ming-Tan Chen, Shep Doeleman, Heino Falke, Michael Johnson, special thanks to him, he's one of the co-chairs, Mariki Homma, Saverana Jorstar, Judy Kuvalet, Priya Natarajan, and Marta Voluntary. And of course, I would like also to thank the LOC, who has been doing really a terrific job, and John Alberdi, Ilya Cho, Rohan Dahale, Mariana Fosky, Antonio Fuentes, Thalia Traianu, who is the chair, Rocco Lico, Alicia Pellegrina, Ioannis Misterlis, Teresa Toscano, Angelo Ricarte, and Juan Yao Sao. And I'd like to thank all of them, because this has been really a great effort. And with this, I'd like to open the meeting, and we will have first 2 talks. So we will have a talk by Huib van Langevelde, who is the project director of the EHT, and that will be followed by Shep Doeleman, who is the project director for the ngEHT. So.
Okay, I will be brief, so we can get to all the exciting science. The Event Horizon Telescope Consortium has met here the last 3 days, and I look around and I see that a large fraction of you is very aware of that. That is a closed meeting of our team. We have chosen to work on the important results of the Event Horizon Telescope in a team setting, where we discuss and evaluate our scientific achievements very thoroughly before we share them with the world. We have also been discussing in that meeting how we do that, what our practices are, and we recognize that for the advance of science, but also for the careers of our young scientists, we will have to engage more with our peers in astronomy and be more openly discussing our progress. And this is then the first time we start doing that together with the ngEHT project. And we are extremely happy to have this opportunity. And we are, as a director, I'm also very happy that we have a large funded project to look at our future options to focus further on black holes and how they work. And as a scientist, I think we have a responsibility to make sure we do that collaboration justice and work towards the best possible results. So today we will focus first on the Sagittarius star and hear about that. And although I'm not a black hole expert, I originally worked on mason stars in the galactic center. Sagittarius star and me go back a long time. I can testify that in my first 1990 field BI observations, Sagittarius star was included. And for doing L-band masons in the galactic center, Sagittarius star is a really lousy calibrator. So we will not, I would not have thought that we could zoom in all this way, and Heino really had to convince me that yes, this was possible. And he stands right, I stand corrected that you actually can resolve Sagittarius star. Actually, I was working on stars around the galactic center in the radio that the gravity group does now in infrared much better. And when I was talking to the press about the possibility there was a black hole in the galactic center in 1992, the senior members of my institute in Leiden came and said, you cannot speculate openly in the press about the existence of black holes because we really don't know that they exist. And I'm very, very proud that I've been part of one of the building's cornerstones to prove that. So before we go to the science, I want to acknowledge that because these are back-to-back meetings and these are the first times we travel and we have COVID, things have been a challenge. People have been forced to come to this meeting during the weekends and make a very long week out of it. I think that was the consequence of a very busy summer and the fact that we all wanted to get together with all our teams. And I want to especially acknowledge the fact that that puts also a extra burden on the local organizing committee. You just have applauded 5 minutes ago for the local organizing committee of the ngEHT meeting. We closed the EHT meeting somewhere today in a rather diffuse way. So please can we also now have an applause for the local organizing committee of the EHT meeting. And that of course includes the SOC chair. Shep, you want to give your perspective on today? Thank you very much.
You just flip this on. Can everybody hear me? Yeah. So this is a very special time. You know, we're here together after a long hiatus, and this is the merging of two meetings, the EHT and the ngEHT, and it's very fitting because the ngEHT, which is kind of what comes next, is something that's built on the EHT. It really wouldn't exist without that. But the EHT has really opened our eyes in a certain way, and it's allowed us to dream again. The EHT itself was a dream. I remember I used to be the youngest person pretty reliably in the room when we were first thinking about millimeter VLBI. Now I'm pretty reliably the oldest person in the room. And the EHT has allowed us to dream because now we know that shadows exist. And we didn't know that before. So now we can fine tune anything we do in the future to this kind of geometry. We know that the space-time of the black hole is laid bare. And the second thing we can think about doing is putting new dishes anywhere on the globe. So the secret sauce of the Event Horizon Telescope was that we were able to take existing dishes and repurpose them to do something that no one of those dishes could do by themselves. And now we can think expansively about what to do over the next decade. And to do that, in my view, we need three things, right? First, you need a really visionary science case. And of course, we have that. This image here can be decomposed into multiple orbits around the black hole. It's not just the lightly bent photons around the black hole in the space-time, but there are photons that make U-turns and full orbits. And these encode very, very strongly the space-time close to the black hole. And now we can tailor our observations and our next generation instruments to think about that. And more than that, we can make movies of black holes. So by taking many frames on M87, for example, we can see the energy flow from the black hole through these well-collimated jets. And the second thing you need is a technical challenge. Everybody here loves a challenge. We're here because we wanted to do the impossible. We're here because we want to dream about the next stage. Going from a few tens of petabytes to hundreds of petabytes, processing all that data, making movies. These are extremely interesting challenges. And not just on the technical side, not just on the software side, but also thinking in a dramatic way about simulations and ways to test new theories. And the third thing you need, and how brought this up, is a team. You need an amazing team. And thankfully, we're starting with the Event Horizon Telescope, wonderful group of scientists, mathematicians, even philosophers, astronomers, all coming together to study the black hole and to study these on horizon scales. And I want to give a very important shout out to the early career people here, because the lifeblood of the EHT and the ngEHT is and has been the young people who bring immense creativity and immense drive to the entire project. That's what will drive us forward over the coming decade. So we're going to describe to you all the science we've done with the EHT, what's to come with the ngEHT. And the nice thing about the ngEHT is that this is going to be the legacy of the young people here. This will be their instrument. So having them involved deeply and in an integral way is absolutely fundamental to the entire project. So I look forward to everything to come for the remainder of this week, and the pedestal on which it sits, which is all the science we're going to see. And I'm just absolutely tickled that everyone's here. So thank you very much.
Okay. And so let's first
just
give
2
a
minutes.
hand to the LOC for Talia.
Yes, a short warm welcome from the LOC to the ngEHT meeting. So a short summary of the registrants of our collaboration meeting. In this, there are 135 registrants so far, and we have 53 requested talks, 5 posters, people from all around the world. Here you can see in the map where registrants they came from, and some useful information for you is the Wi-Fi password. Password is the one in the screen, and the one that we are posting in. We have posted in Slack, and we are going to post it again later on today. We have 3 breakout rooms for the parallel sessions next days. Marie Curie, which is in this floor, and Carl Sagan and Albert Einstein, which is in the upper floor. And also, if you want to charge your mobile or your laptop, there are charging stations in the upper part of this room. Thank you very much and welcome.
Thank you, Talia. Now let's start with the recap of our recent publication results on the Galactic Center. We start this 1 hour session with Jeff Bauer from the management team to give us an overview. And each of the talks will be about 10 minutes and we leave room for 2 minutes of discussion.
Okay, good morning, everyone. It's a pleasure to see all of you here. Of course, all of my ngEHT colleagues who have been here for several days already, and many of my friends and colleagues from the VLBI and black hole world who are a part of the ngEHT. Oh, can I have the clicker? Oh, it's not working. Okay. I see. Okay. All right. That will constrict my ability to roam around the stage, but we'll make do. Okay. So I'm very excited to be able to share with you the results of the ngEHT on Sagittarius A star. You're of course all familiar, I think, at this point with both of these sets of results. That the image of Sag A star and the image of M87. Is that going to work? That works. Okay, so these images are the images that have launched 1,000 memes, and by far the one that I'm most proud of is the appearance in the XKCD comic, because that's on everyone's short list of things to accomplish, but also because it tells us something about the physics of it, as well as providing interesting commentary, right? And that the size of that ring is comparable to the outer diameter of the solar system. Whereas for Sag A star, 1,600 times less massive, the size of the ring is comparable to the orbital radius of Mercury. As both Huib and Shep have emphasized, this is a huge team effort. Here's the conference photo from the last time that the ngEHT was all together 2.5 years ago in Hawaii. And of course, the very hard work that we've done over the last 2.5 years to produce these Sag A star results has been done virtually, which has been an enormous challenge, and I'm incredibly proud of our team's efforts to work virtually. But it's really, really terrific for all of us to be here together. So for those of you who are ngEHT people and not participants in the ngEHT meeting, you can take a look at this photo and identify many of the people who are present here who are ngEHT contributors. And I'm completely proud and excited about the fact that half of our attendees are early career members. Okay, so the motivation for the Event Horizon Telescope is well known: to make images of black holes. The two black holes that are accessible to us are M87 and Sag A star. They are the largest angular size black holes on the sky, and through a fortuitous coincidence, they are also among the two brightest black holes available to us. And so they sit in a parameter space that is accessible, but is nevertheless extremely challenging to reach. The shadow diameter is on the order of tens of microarc seconds, much, much smaller than an angular resolution that can be achieved by any instrument, any other instrument. About 20 years ago, there was a very clear prediction for Sag A star and subsequently for M87 that the shadow was an observable feature. And through the following decades, there's been continued evidence, incredible growth in theory in terms of simulating what we might see. But nevertheless, the shadow remains a persistent feature regardless of the astrophysics that we put into the simulation. As I've noted, these are extremely technically challenging observations to carry out. And there are a number of factors that contribute to that. We need that ultra high resolution, which means that we need short wavelength observations that span the globe that give that high angular resolution. That means we're working in some really extreme locations with, so for instance, the submillimeter array on Mauna Kea, and you see the other locations around the world. And we are sensitivity starved. And that means that both the growth in recording bandwidth that's taken place and also the introduction of larger and more sensitive facilities such as ALMA have been really transformative for the array. This is what observations of Sagittarius star looked like over a decade ago. A free baseline interferometer measuring a visibility amplitude curve and fit with a Gaussian model. That's the best that we could do at that time. It was quite significant, and it set the scale of the source to be comparable to the Schwarzschild radius or a few Schwarzschild radii. So now let me show you a little bit about the galactic center itself. So we're zooming in with a radio view of the galactic center, and here we are in the galactic center, and you see this incredibly rich regime in which the Sagittarius A star exists, the large supernova remnant, the mini spiral of gas, ionized gas that's spiraling in, some massive stars, and here is Sagittarius star buried amidst all of this. Sagittarius star is in a low luminosity AGN at the extreme end of low luminosity AGN, very underpowered, very low accretion rate, very unusual or not typical of the other AGN that we look at. Of course, what makes Sagittarius star so incredibly special and distinct from M87 is the precision with which we know its mass and distance. We know its mass and distance to an accuracy of about 1% as a result of the incredible work done by the Gravity collaboration and the UCLA collaboration, which were both honored with a Nobel Prize 2 years ago for their work. And those measurements provide this extraordinary precision. I will note, which is actually in each measurement better than 1%, I will note that there is still some small discrepancy, systematic discrepancy between the two results, but that doesn't affect our interpretation at this stage. So this is what VLBI data looks like now, visibility amplitudes. As a comparison against what we obtained over a decade ago, and you can see how much richer this data is. And so for those of you who may have some misgivings about the complexity of interferometric imaging algorithms, I want you to focus on this chart, because as a physicist, as an astronomer, you can read off so much information from what's present here. So visibility amplitudes are the Fourier transform of the brightness distribution on the sky. And you can see this ringing structure, the appearance of two nulls, which is clear evidence for sharp structures. And in fact, this is a Bessel function that's going through here for a ring that corresponds to a ring with a diameter of 50 microarc seconds. And you can see how the data follow that. In the case of M87, it leapt out immediately. It's a little bit messier for Sagittarius star. There are a couple of things I can point out to you. You can see that some of the visibilities go into the null, but not all of them. That's suggestive perhaps of orientation effects, or perhaps that's the result of dynamics in the system. Something very difficult for us to disentangle in this data. I'm not going to have time to go into this in my talk, but you're going to hear extensively about this in the coming talks. There are two really major challenges in the imaging of Sagittarius star. Scattering due to turbulent interstellar plasma along the line of sight, and temporal variations. Sagittarius star is smaller, and so it evolves on a time scale of tens of minutes to hours, the same time scale on which we're obtaining our data. So here is the image, and I want to emphasize to you that we really, if we really want you to think about this as representative and not the only image, not the only thing that can be achieved from this. The key thing to focus on is that the ring diameter is consistent with the predictions of general relativity in the Kerr metric, and that we have very high confidence that this is a representative image. At a few percent, there are all possible alternatives of non-ring-like structures, but it's a very low probability. You'll hear about the theoretical interpretation of this in terms of astrophysics. The main thing that I want to emphasize is that we applied a wide range of astrophysical constraints, and none of the models can meet all of the astrophysical constraints. That puts us in a regime of doing precision astrophysics on black hole accretion and outflow. Additionally, we're working in a regime where we're able to make tests of general relativity and black hole physics and gravitational physics. We occupy a unique part of the overall parameter space that separate from LIGO, separate from solar system tests, separate from cosmological tests. And we operate with Sagittarius star and M87 over 3 orders of magnitude in mass. All right, so that's the end of my talk. I want to emphasize a few points to close here. What have we learned? Black holes power active galactic nuclei, sitting at the base of relativistic jets and sitting in the nuclei of ordinary galaxies. There are black holes. As I said, we're testing general relativity over multiple orders of magnitude. We're doing precision measurements. What is the future? The future is incredibly bright. We have an enormous amount of data that we've already obtained that we will obtain in the coming years that's going to validate our measurements, improve the accuracy, do accretion and jet dynamics, time sample measurements, imaging, movies, so forth. And we're really establishing the foundation for future ground and space-based VLBI of black holes. Thank you.
Thank you, Jeff. While Kazu is coming up here, we have time for a few minutes for questions or comments. Anybody? Comments, questions? Okay, if not, I thank again Jeff for the nice intro and hand over to Kazu Akiyama, who will tell us about the observations and imaging process on behalf of the working groups behind that work.
Can you hear me okay?
All right.
Okay. Hello, everyone. My name is Kazu Akiyama from MIT. So my talk will focus on this image, the imaging process of the ngEHT Sagittarius star data and how we made it this image. So before diving into the details, I just want to emphasize that this work is not done by just a handful of people. This is literally the non-stop work in the last 3 years by an amazing 100 of scientists in our ngEHT imaging working group, led by José Luis Gómez here, and Katie Bauman, unfortunately not here today, and then also myself. So before going to the Sagittarius star, let me just give a quick recap of how we make images with ngEHT. All right, so this is the case of our M87. Anyway, so ngEHT is interferometer. So we are not like the camera, and we are sampling the information of the on-sky image in the Fourier domain. And we have a virtual planet-sized dish in a Fourier domain, and we actually collect the information, and that actually constraining the images or structure on the sky. But we have actually two important points here. So first of all, we don't have a perfect coverage in the Fourier domain that actually causing the ill-posed issues. So there are infinite number of possible images can explain our data, so we need to explore that. And another thing is the Earth rotation is very important. You know, with Earth rotated many telescope join that actually help to sample many points in the Fourier domain. And also the Earth rotation will change the projection of the baseline connecting each pair of antenna. And that allows even in a single baseline can sample many Fourier points. But so here the fundamental assumption is, you know, we are observing across night, collecting the information of the source, but all single data point is coming from the same image on the sky. But this actually gives a really big challenges for Sag star. We have two daunting challenges. The first one is obviously time variations. The Sag star is very variable, changing its appearance on the time scale from minutes to hours. So every single minute, you get the data coming from a slightly different appearance on the sky. This is very challenging. And other one is the scattering. This is actually pretty minor effect in our observing wavelengths, but this is coming from its unique location. It's hiding in the center of our galaxy, so we need to look through our Milky Way. And unfortunately, there is a stochastic turbulent plasma actually scatters radio waves along the line of sight, and that actually causing the slight blurring of the images. And if you have a really, really good eye, you can probably see some persistent substructure here that is coming from the distortion from the scattering. Anyway, this is actually pretty minor effect because you can see still, the overall like a structure is preserved and you can see the ring. So this is actually really seen in the ngEHT data. So I just showing the M87. These different colors are coming from different baselines. Anyway, you can actually see that, that each baseline is showing a pretty packed data points. And actually, this is the case for Sag star. It's really scattered. I mean, this is actually coming from the Sag star. It's really time variable. We assess this actually, but in paper 2 and paper 4 with the various metrics. And Dom actually will slightly touch about this in the next talk. But yeah, we actually see the time variation in the Sag star data. So how we handle actually these challenges in the imaging process? So actually, our imaging paper explore a multiple method actually, and then that actually gives the consistent results, assuring our results. But the main product is coming from this approach. So yes, we are observing the movie on the sky, but this can be described as a summation of just the time average morphology and the residual. It's a dynamical component. And this is the same in the Fourier domain. What we are observing can be described as the Fourier component from the mean structure and some like a stochastic time variable component. So what we made is that we made a statistical model for actually the time variable component, and then infer what is the mean structure on the sky across the night. There's a very nice work done by the José actually in the collaboration meeting now, and also Avery Broderick, and also the fantastic work done by paper 14 actually constructing this model. But we actually also applied this in the imaging method. We did the same thing actually for the scattering. What we did is, first of all, we actually reconstructed images without any mitigation of scattering effect, just as it is. And also what we tried is, this scattered images can be decomposed into two components. What is the first one is the just blurred image, and also the residual is actually the stochastic distortion component, the so-called refractive substructure. And this blurring effect can be perfectly described by just a simple convolution of the on-sky image and the scattering and blurring kernel. And the good news is we have a decade of radio observations, and we know what is exactly the scattering kernel is, and what is the statistical property of this noise component. So we are using actually this statistical model for this component, and also we just completely solve actually for the blurring effect, and then infer what is the intrinsic sky structure. So these actually two approaches are implemented in the 4 independent imaging method. The first one is the inverse imaging method, so-called CREAN. This is a community-wide standard, used in the last half of century. We also have the 3 imaging method dedicated for the ngEHT using the 4 imaging method. The first 2 are employing the regularized maximally likelihood ngEHT imaging library and SMILEY. And then also we also have a new the Bayesian imaging method exploring the posteriors of the images. Anyway, so all 4 imaging method employing actually this kind of mitigation method. And we explore a bunch of images. So what we did is we export, I think, into like 100K of the combination of imaging parameters that basically reflecting the imaging assumptions. And what we did is we test each single combination of imaging parameters with the series of the synthetic data with a very similar properties of time varieties and also with a different morphologies. And then we actually pick, we evaluated the parameters and picked the combination of parameters that can actually distinguish different morphologies very well and apply to the Sagittarius star. So that actually made, that made 1,000 and 1,000 of Sagittarius star images, and all of the images are consistent with the EHT data, but they are a little bit different because this is coming from different assumptions. Anyway, if we average all of the images to see what are the common feature, and yeah, that actually gives really beautiful, actually this ring with a diameter of 50 microsecond. So let's just go back to the image distribution. As I said, the images are a little bit different. So we actually cluster and group all the images into 4 groups. Then yeah, the vast majority of the images are showing the ring with exactly same diameter. And just only few percent of images actually showing the morphology without a ring. Anyway, the vast majority of the images are reconstructed with a well-vetted method that actually shows the ring with a consistent diameter. So let me just give a just quick note about this. So we really cannot, exclude this possibility, just given the principle of the radio interferometry. However, actually, we think that the evidence for the ring is pretty strong. So let me just think about like this. So what actually we are looking at actually in this image distributions. So one possibility is, no, all the ring is a fake, and this is the true nature. And so we actually found that this is really unlikely. We tested, we applied the exactly same method to the synthetic data with the various ring morphologies. This includes geometrical, GRMHT, but as far as data have a similar the properties with EHT data, that actually reproduce our results. And then another thing is that we can do the inverse thing. And what we found is that, yeah, non-linked images appear as just the non-linked images as the majority. So we really don't think that is the possibility. And for the scattering, we actually reconstructed images without mediation. We still actually have a major amount of rings and also different scattering mitigation method actually do not produce a different distribution. So we also think that we also confirm that scattering is not the matter. And so the final possibility is the most likely case. So just we are observing the time variable rings, and because our coverage is very sparse, just this non-link mode just appears on our uncertainty. So that's why we think the EHT 2017 Sagittarius star data have a compelling evidence for the presence of the ring with a diameter of 50 microsecond. By the way, yes, this is the 5 radii. This is expected for the diameter of the shadow of the black hole enclosed by the ring of photons, which is pretty much exciting. So this is the ngEHT reading. So I just want to show this one. Obvious the science target for the ngEHT is resolving dynamics and getting a beautiful movie of Sagittarius star. We actually made a very first baby step in our data. Here what I'm showing is we actually did imaging and also modeling, but I'm showing just the imaging results. So this is April 6th and this is April 7th. This is the time zone. We have a very good UV coverages. And what you can see is so this is the video actually reconstructed with different assumption for the degree of time variations. What you can see is that in April 6th, regardless of our assumption for the time variability, the structure is pretty similar. But April 7th, we started to see, if we allow more time variability in the data, you start to see like some flip in the brightest point in another way. Although actually this is not conclusive because if we actually constrain time variability more, then you have more static reconstruction, that still explains data very well. So we actually do not have a very good coverage enough to uniquely constrain the dynamics. Anyway, we started to see something very different between April 6 and 7. That's a kind of glimpse of the dynamics in Sagittarius already seen in the data. So we started to make a first step actually toward the future reconstruction of movies in the next generation of EHT array. So I just want to stop here, and I'm happy to take your questions.
Thank you, Kazu, for this challenge to compress the many results in 10-minute talk.
Yes, this is actually 100 pages.
We appreciate that. We keep the time. Are there any questions or comments? Please raise hand so that I can see it. Yeah, over there.
No, actually, can you say again, please?
So almost all the ring morphologies had a ring that was filled with more than bright spots, except for that double source looking representative of the non-ring image. But even that double source could be deemed a degenerate ring, but it's just a ring where it has 2 points that are, it seems like 25 microarc seconds from the sensor. It seemed like it was the same radius. So are there non-ring quote unquote images that don't have the brightest spots where a ring would be if it were more filled out, or is it in fact a degenerate ring? Does that make sense?
Yeah, so first of all, I just want to clarify that the ring mode actually are really showing the ring with the same diameter inside the cluster. But for the non-ring mode, actually, we have a wide variety of images. Actually, some of them have double sources, but that also includes just a single blob, or more like just the 3 blobs. I mean, the kind of a corrupted ring. So it's actually, first of all, we have actually a wide variety of possibilities there. Not really. I probably don't too much focus on the mean image, because we average over the multiple actually different morphologies. But I just want to emphasize that every single actually the non-ring image still actually can explain Sagittarius star in a very good way. So we cannot exclude the possibility. But still actually we think that that is not reflecting the true nature on the sky.
Okay, thank you. I think we have to move on. Thanks again for the speaker. So we are moving on for the variability morphology and black hole mass and the interpretation from variability. So please, Dom, go ahead.
All right, thanks, Thomas. Thanks, Kazu. Yeah, so I'm Dom Pesci. I'm going to be talking to you today about the 4th paper in the Sagittarius star series, covering the variability morphology and black hole mass. My co-coordinator, Roman Gold, couldn't be here today, but I do want to just point out that he is somebody without whom this paper would not have been possible. And other people as well. This paper is the result of work by a large number of people, and I'm going to actually be highlighting quite a bit all of these individuals in my presentation today. I think most people in the audience here have at least some sense of the science that's come out of this paper and the others in the series. You may be somewhat less aware of the human story behind a lot of that. So I'm going to try to give a little bit of perspective on that today. So one of the first goals of this paper was to measure, quantify the morphology seen in the images that Kazu just told us about. We have a couple methods for doing that. The first one is inherited from the work already done in M87. This is a method called REX. It's a way to kind of non-parametrically identify features in and sort of measure them, things like the ring diameter and width in these images, sort of walking around a ridgeline like that. And the other one is a more parametric method, a way of describing the image in terms of templates and doing a sort of template matching scheme to find which parameters of the template best match the image. This is a scheme that's a particular one, something Vita. So Rex on the left, developed by Andrew Shale, Vita on the right by Paul Tita. The people in charge of these in the paper 4 analyses, Utero, really key for getting the Rex analyses done, and then Paul Tita for Vita, and combining both of them, building the full pipeline. Inyan there in the center is somebody who really spearheaded this particular analysis, the image domain feature analyses for this paper. The other way of quantifying the morphology from the data here directly rather than from an image is there's something we call geometric modeling, where we parameterize, again, the source structure in terms of sort of simple models, but then fit the data directly in the visibility domain. And I'm going to talk a bit more about how we do this later on in this presentation. But one of the elements of this geometric modeling, or something that lets us do very nicely, is to try to motivate the particular source structures that we would expect to see in an image. And this is a pair of panels showing an exploration of simple geometric models for which we compared this quantity on the y-axis here, this log Bayesian evidence quantity, which indicates a statistical sort of preference for a particular model over another. If there's a higher value of it, it indicates some sort of preference here. And the two sort of flavors of points on these plots, the open rings and the X's, indicate respectively the models that are ring-like in nature and models that are not. And for every level of complexity measured here by the number of model parameters that we explore, we find that ring-like models are preferred over non-ring-like models with a comparable complexity. This is an analysis that was led by Frake. And this is something that we think is more evidence for there really being a ring in these data. And it motivates in part the structure of the geometric model that we're going to use to actually do the measurements, carry out the quantification of this morphology. In this case, we use something we call an MG ring, has to do with the particular components used in the construction of the model. This comes from work that was actually originally led by Michael Johnson, and it's a bit of an evolution over what was done in M87. Instead of a simple crescent model with a brightness gradient for Sagittarius star, we found it was necessary to include a model with somewhat more complicated azimuthal brightness variations, and that's the primary difference between this model and the previous one, is its ability to encode arbitrary levels of azimuthal brightness variation. The challenge for all of these analyses, of course, as has been mentioned several times now, is that the source Sagittarius star is highly time variable. This is a simulation from one of the GRMHDs. And if we have a variable image, we of course have a variable Fourier transform as well. And I find it personally quite helpful to think of this Fourier transform to remind myself this is really not just an image, this is really a Fourier landscape that we have access to. But our data, unfortunately, only see a very small part of it. So here now I'm showing a single snapshot of our coverage and how, which regions of the Fourier transform there we're really sensitive to. And we do gain access to many independent Fourier samples by virtue of this Earth rotation aperture synthesis. But as this animation is showing, there's this unfortunate property when you have a time variable source that although you get independent Fourier samples, each of those samples, or many of them, are sampling independent images. So you aren't able to sort of aggregate the information in the same way that we normally do. And this is the crux of the challenge here for any sort of analyses on the Sagittarius star data. And I'm going to progress the slide here in just a moment. And what's going to happen when I do that is that background grid that's being used on the right to guide the eye is going to fade away. And I'm going to add a variation to all of the data points on the right of a magnitude that's relevant for the noise uncertainties in our measurements. So you're going to see how the data sort of actually look in some sense. Again, this is a simulation. So you see the sort of bouncing without anything to guide the eye there. It's very messy looking, very chaotic. And something that I think is actually really important to stress here, because it's somewhat, I think, not emphasized elsewhere, is that as we look at these, that there's a real similarity between the real data and the simulation that I'm showing here in these variable data. I actually switched over halfway through this animation from that simulated data to the real data, and I sort of challenge you to find where exactly that happened. It's really hard. They look almost identical. And this is something that I think is a testament to the simulations that we're running. So difficult to do these analyses, but we can start by trying to quantify the amount of variability in them. And that's what this was being done here. We can bin the data points in time and in space to measure their variance. And that's plotted here as a function of baseline lengths, of binning them azimuthally. We see this approximately power law decline that we think is a good measure of the power spectrum and the variability in this source. On the longest baselines, above about 6 gigalambda, we think that this variability that we're measuring is dominated by both thermal noise in the data and by the refractive scattering. So it's not reflecting intrinsic variability in the source. But on these baselines between about 2.5 and 6 gigalambda, it is in fact something that agrees extremely well with the simulations that we have. And this runs a little bit counter to this notion of a variability crisis. It is true that the simulations overpredict generically the amount of variability seen and in the integrated light, in the light curve in an unresolved way. But on VLBI scales, the Sagittarius star data, as far as we can tell, look an awful lot like these GRMHD simulations. So when we hear about the problems with the variability, I just want to emphasize that there's flavors of that, and we don't have problems in every respect. The spatially resolved variability actually seems to match really well. This is stuff that spearheaded the sort of understanding of the GRMHD simulation variability, something that was spearheaded by Boris up there on the left, and the measurement technique used to extract this from the data by Avery up there on the right. All right, so we have this variability. We know its magnitude approximately. How can we model in the presence of it, or image in the presence of it?
The first approach we do is, I think, conceptually the simplest, something we call snapshot modeling. We segment the data into very small chunks over which we think the source is static. And then we apply static modeling. And we do this to every frame of the segmentation, and we average the results to get the average source structure. This snapshot modeling in this context of paper 4 is something that was led by Freek, Ha, and Paul Tita. And these folks fit various geometric models to the SAGI-STAR data and carried out this procedure. The other one is one that Kazu already mentioned, what we're calling full track modeling. This is where we fit the entire data set at once. We construct a model for either an image or a geometric model for the mean source structure, the average source structure, and then we have a parameterization or a characterization of the residual variations about that source structure. In the case of paper 4, this was led by a number of people here, primarily Roman Gold spearheading this thing, but with substantial contributions from Razi Amami, Chiara Cecabella, and Kai Li. And for the full track modeling in particular, we have to have a prescription for that variability. Like I said, this is something we augment the data uncertainties in a particular way. So in addition to the thermal noise, we add in components that deal with the systematic calibration uncertainties and the refractive components. But this last one is this variability noise component. This is something that we parameterize based on an expectation from the GRMHD simulations. Over there on the right is a measure of the power spectrum of variability from all of the GRMHD simulations that Boris analyzed in his companion official paper. We see this characteristic broken power law spectrum there, which we can characterize or we can parameterize as shown here in the slide. There's a number of free parameters there, A, B, C, and U0. These are actually fit alongside the parameters describing the source structure. And this is how we accommodate the variability during the full track geometric modeling. This is work again, led by Boris. Doing all of that, all those image domain feature extraction and geometric modeling techniques that I just described, we end up with results. We end up with a quantification of various parameters of interest in the source. On here in the slide, I've pulled a plot from the paper. It's a little bit busy. It shows points across a number of data sets, days, bands, measurement types. But on the top is the diameter, on the bottom is the width. These are parameters that we think we can constrain fairly well from the data. The diameter of the ring is pretty consistently about 52 microarc seconds. The width of the ring is pretty consistently between 30 and 50% of that diameter. So these are quantities in the morphology we think we have good access to. There are other quantities that we've attempted to measure, things like parameters describing its asymmetry, the magnitude there on the top and the orientation on the bottom, that vary pretty widely from method to method, or that have extremely large uncertainties in any particular method. These are parameters we would have liked to have really good access to, and we don't think we have a good handle on from these data. And I do just want to give a shout out to Paul Tita again here, who really did the hard work, the thankless work of aggregating all of these measurements and putting them into these nice figures for the paper. But the diameter is one that we care the most about. The diameter is a parameter that relates to the mass of the black hole, or more specifically to the mass to distance ratio, which we encode as the angular size of the gravitational radius here. We think that these two things, the diameter and the angular size of the gravitational radius, are related by a simple scaling factor, this alpha up here on the slide. This is exactly what was done in the M87 papers as well, paper 6 of that series. And the way in which we don't know this alpha a priori, and the way in which we derive it is using a prior on the distribution of emission, which we get from the GRMHD simulation library. By carrying out our analyses on data sets produced from that library, we can calibrate this alpha scaling factor. And this work, the synthetic data used to perform this calibration, that generated by Cotro, and then Paul again running the actual calibration itself. The results here are shown for all the measurement methods. We get a pretty consistent angular size of the gravitational radius of about 4.8 microarc seconds. That's just one step away from a mass. We take the distance, multiply it in, and we find that the mass of 4 million solar masses very consistent with what is seen from stellar orbit modeling. So that's it. Summary up here. The folks again right here. Thank you.
Thank you, Tom. Thanks for the nice review of the very interesting methods to model fit data. Questions, comments? Please raise hand over there. Just wait a moment until the mic is.
I mean, that's just cruel up there.
Yeah, thanks for a great talk. I'm Jonas, a science writer following the ngEHT. Just a question about mass. So the mass gives you the size of the black hole shadow, but do you also get the prediction from the ring width from the mass? And is that something you can use in the analysis?
So you're asking if the width of the ring is related to the mass of the black hole? I would expect that it, as the whole system kind of scales up in size with the mass, in some sense, the absolute scale of any size in the system should scale with the mass. We didn't use the width in this analysis to do any constraints. This is entirely done with the diameter.
Any more? If not, we thank the speaker again and we move on to Michi Bauberg for the astrophysical interpretation and deeper insights, what it all means.
Start off maybe not with the conclusions, but from the beginning. All right, thank you. All right, thanks. Okay, so I'm here to tell you about the astrophysical interpretation, namely what can we learn by looking at all this amazing results that we have now about Sagittarius A star, and what can they tell us about the accretion flow around the black hole, and these sort of open questions about that accretion process. And the way that we tackle this question is via GRMHD simulations. We built a huge library of GRMHD simulations that we can then compare to both the EHT observations of Sagittarius A star and as well historical observations to see which models are consistent with what we see. So let me give a brief overview of this library that we built. We split our library into two kind of groups. I'm going to talk first about the fiducial models, and mainly in this talk, I'm only going to mention the fiducial models, which are sort of the standard, the normal GRMHD models, which have a thermal electron temperature distribution, an aligned torus, so where the torus of the initial torus that we use as an initial condition is aligned with the spin axis of the black hole. And then we can vary the spin of the black hole. We can vary the inclination, so the viewing angle that we see this accretion flow at. We can vary the electron temperature parameters. So we parameterize this with this R high parameter, which essentially tells you how hot or cold are the electrons in different parts of the flow. Is the disk hot or is the jet hot? And then we can also vary the magnetic field. So we have two classes of models called MAD and SANE. The MAD models have a strong magnetic field where the gas pressure in the plasma is roughly comparable to the magnetic field pressure. So the magnetic field is dynamically important and can push the plasma around, as opposed to the SANE models, which have a much weaker magnetic field, and the magnetic field is dragged along with the plasma rotation. So we varied over all of these parameters, and we have three separate GRMHD codes, Karma, Bach, and Hammer, which ran over the same parameter space. So we have multiple redundant versions of each model that we can use to cross-check to make sure that they are consistent. I'm just gonna give you this. This is only a fraction of the models. Actually, this is all from one code. So this is just the Karma code. These are images from some of the models that we use. Again, this is only a fraction of the total. In addition to these, what we've called fiducial models, we have exploratory models. These are models that make some other assumption, a non-standard assumption about the accretion flow. This includes things like alternative electron heating prescriptions, either a thermal prescription that is not the R high prescription, or adding non-thermal electrons via some sort of kappa distribution function, for example. We have some alternative geometries. We have geometries where the disk is not aligned with the spin of the black hole, for example. We have models that are motivated by the neighborhood of Sagittarius A star and using the stellar winds from the stars near Sag A star to feed the accretion flow. And we have different, we have other codes that focus on running these models for a long time over a much smaller parameter space. Then what constraints are we comparing to? We came up with a list of 11 constraints total. 5 of those are derived directly from the EHT observations. These are things like the size of the image, the location of the nulls in the UV domain, these M-ring fits that were just described give us constraints on the diameter, the width, and the asymmetry of the ring that we see. In addition to that, we have several constraints that are not directly related to the EHT observations. We have historically, we've had different observations at other wavelengths. We have 86 gigahertz data. We have 2 micron data in the infrared. We have X-ray data. We have an image size at 86 gigahertz. These are all things that we can predict with our models. And so we compare the predictions of our models to these data. And then the last two constraints that we use are constraining the variability. And we did this in 2 ways. The first being just looking at the flux variability at 230 gigahertz. So we make a light curve of our models and we compare the variability in that light curve to the variability that we see in the actual light curve that we observe from Sag star. And the second is looking at the variability of the image morphology. So we can look at the variability in the visibility amplitudes and compare that to the variability in the images from our models. Let me start off with variability. This is the so-called variability crisis that all of our models, or the vast majority of our models, overpredict the variability of Sag star. You can see if we just apply the variability constraints, I'm going to be showing a few of these plots so this is the whole model space. Red fields correspond to models where all 3 of our fiducial codes fail that model. Yellow are models where some of the codes pass models and some of the codes fail. And green are models where all 3 of the codes agree that the model passes. And you can see just applying the 2 variability constraints, we've already ruled out almost all of our models. So something is missing from our codes. There's obviously some physics that we need to add to our codes to account for the fact that Sagittarius A star is apparently less variable than what we predict from the GRMHD. So given that these 2 constraints alone eliminated almost all of our models, we decided to proceed and ask, what can we say from all of the other constraints? So leaving out the 2 variability constraints, this is now the 9 other constraints that we applied. So everything from the EHT images, the ring, the size, the width, the asymmetry, all of the multi-wavelength constraints. And you can see that we rule out, again, almost all of the models, but there is a small region of the parameter space that seems to work, where our models can match all 9 of these different observational properties that we have for Sag star. So let me just give that to you in a different visual way. So this is the same series of fiducial models that I showed you at the beginning, and we're going to cut out the models that fail at each stage. So this is those were the 2 EHT constraints, the size and shape of the ring. This is the models that fail some other part of the spectrum. And then this is those were the models that failed the size at 86 gigahertz. And we're left in this case with these 2 models that we're calling best bet models. And these 2 models, I want to emphasize, do a good job. So our cuts are always very conservative. We try to allow models every chance to pass. We only cut the models that are really far from the observational constraint, from the observations that we have. But the 2 models that are left in the end look good. They're not just barely scraping by our constraints. They seem to fall pretty much in the middle of the measurement for all of the constraints that we have, except again, the variability is that M3 parameter in the bottom right. And you can see that both of the models overpredict the variability. Also in each of these plots, there's each violin plot is split in half. There's a left side and a right side, which are comparing 2 of the codes that we use. And you can see there's really excellent agreement between the 2 codes. They're consistent, and we think that we have a good handle on the predictions made. So let me leave you there. We have, I think, surprisingly, maybe, given the wide range of constraints that we're trying to match with our models, we have models that work well and that can really match what we see and describe Sagittarius A star as observed over a wide range of wavelengths and properties. The caveat to that is that variability is hard for us to match. Our models on the whole are too variable. And this is something we're working on right now. We're trying to figure out what additional physics we can add in to those models that could reduce the variability. And then the sort of trends among the best fitting models are that those models seem to be MAD, that is strong magnetization. They seem to be low inclination. We seem to rule out edge-on models and favor more low inclination models, not necessarily directly face-on, but not edge-on at least. We favor models with a large R high, meaning that there's a large difference between the electron and proton temperatures. And we seem to favor models with a prograde spin. So those models where the spin of the black hole is in the opposite direction of the accretion flow tend not to work against the observations. So I'll stop there and take questions. Thanks.
Thank you. I see a number of hands up. Shep first, please.
Yeah, very nice. Very nice. Very nice. Can you say something about the jet? If there is a jet in Sagittarius star, if some of the models you have, we would expect to see a jet.
I can say that the model work have a jet. Whether we can, we don't, I guess we're not surprised that we haven't seen the jet in the images that we have so far. Whether that jet is something that we can observe with sort of higher resolution, yeah, still to be determined. I'm not sure.
Okay, Huib was first.
So this is really the question that I get when I give presentations about this myself, and I'm not the expert on. So what we derive are a couple of characteristics that are quite similar to M87, in particular inclination. And yet, when people look at the M87 image, that looks much more asymmetric in brightness than Sagittarius star. How do we reconcile that?
That's a good question. I don't know off the top of my head. I'm not. It's hard to. One of the challenges in this work.
But I assume we derive a low inclination by the fact that there is no brightness asymmetry in that image.
Yeah. So I'm not as familiar with the M87 work. I only joined the collaboration after that was all published, so I can't speak to that. It does seem like the Sagittarius star inclination is maybe constrained by the lack of asymmetry, but I will say this is one of the challenges we face, is that it's very hard to draw a straight line from one,
yes, because
one constraint to one result.
In your figure where you compared the constraints with the data, you said the variability was not very well constrained, but the panel next to it is the inclination, and I think it was also not very well constrained, right?
I'm sorry, say that again?
So, well, your presentation is no longer up. That's a pity. You pointed to the variability constraint being outside of the measurement, but the panel next to it, I think was that the inclination?
No, so we don't have a constraint that is directly on the inclination.
So that was the constraint on asymmetry.
On the yes, on the asymmetry, yeah, which as you can see was very broad, right? Yes. It's hard to, as you can see from the variety of images that we saw just a moment ago, we don't have a strong constraint on the asymmetry, so it's hard to say.
Okay, I think we have to move on. Sorry to interrupt this. There's room certainly to continue on that in the coffee break. Let's please move on and thank the speaker once more. Next presentation will be by Maria Felicia de Laurentiis for the paper 6 on testing the black hole metric and gravity. Please.
Okay. Let's start. I don't know if I am able to recap all paper 6 in few minutes. I will try. Then let's start. Our goal was to test black hole metric, but to achieve this goal, we have to ask ourselves some question, and we asked, now if we relax the assumption that Sagittarius star is not a Kerr, is a Kerr black hole or is not a Kerr black hole, can we quantify the deviation from Kerr black hole? And do we actually see an event horizon, or is Sagittarius star really described by a black hole space-time? And finally, how do our measurement of Sagittarius star fit within the broader landscape of gravitational test? Then let's start and try to answer to these 3 short questions. To quantify deviation from Kerr, we connected the predicted shadow size to an image's diameter and compare into the measured diameter through this equation. This equation was fundamental for us, and all paper started from this equation. Here what we have, dm is the measured ring diameter from imaging and model fitting to the Sagittarius star data. The hat indicated that is measured quantity. Then we have, as also Dom said, we have alpha, that is a calibration factor, is the ratio of measured ring diameter with that shadow diameter, and is determined by physics of the image's formation near the horizon, and quantify the degree to which the image diameter track that of the shadow for underlying space-time and plasma model, accretion plasma model. Of course, the shadow is the shadow. The shadow diameter depend on the property of a black hole, then depend on the metric, spin, and so on. And we have the important factor that is delta is our deviation parameter. With this parameter, we measure the deviation, for example, from GR, and is the ratio of infrared shadow with respect to the shadow for an angular size theta g that correspond to m over d prior. I have to say also that we in all paper we used just alpha. We indicated the calibration factor only with alpha, but we have to say that alpha is a product of 2 other factors. Alpha 1 that came from the ray traced images model, and alpha 2 that is coming from convolving this model with observational effect reconstructed. So we have this, and we use this relation to infer the posterior on the deviation parameter given to the ngEHT measurement and prior information. As my colleague said before, the posterior were derived by the dynamical analysis of S2 star by Keck and VLT. As you can see, the both measurement differ of like a 4%, and we use it both for our analysis to be sure and consistent with the result. Then we calibrated the relation between the geometrical defined black hole shadow boundary and the observed size of the ring-like images using a large library that include both Kerr and non-Kerr simulation. Here we have a fractional diameter difference between the diameter peak emission in the images of a black hole and that of its shadow. The blue histogram show the result of a large snapshot from time-dependent GRMHD simulation in Kerr metric. So we have the orange histogram, we have showed the analytic plasma model in KEHR metric, and the green show the result for analytic plasma model in non-KEHR metric, either in some parameterized black hole metric. And what we see here that all distribution peak at small positive value that indicate that the bright ring is slightly larger than the boundary of the black hole shadow. Then we calibrate this relation for reconstructed model using 3 different imaging algorithms. Again, we have a fractional diameter difference between the diameter of a peak emission in ground truth images and those reconstructed. Here we had 145 synthetic data set. We selected these from numerical, analytic, KEHR, and non-KEHR model. And the image diameter were inferred for all the top set images for the images reconstruction of each data set. Again, we can see that the small offset in the calibration parameter mimic those seen in the analysis of the real Sagittarius data, and the distribution peak at small positive value. So, what we use it as also Dom said, we use it the prior constraint on the mass to distance ratio for Sagittarius based on the stellar dynamics star orbits to show that the observed image size is consistent with the 10% with the KEHR prediction. Here we have the two plot where we have the posterior on the parameter, one for KEHK and the other one for WELT, and the different line are the different model coupled with the different imaging algorithm, and the purple line indicate the 8% range, the 8% of for the predicted GR chemetric, and depend on, of course, on the spin and inclination angle. Here we also we used a combination of measurement and calibration to infer the diameter of the boundary of the black hole shadow, again for different model, analytic KEHR model coupled with the imaging algorithm reconstruction method, and what we see that all are consistent with the observed shadow diameter, and here you can see the inferred diameter of the black hole shadow boundary overlaid of the average of ngEHT Sagittarius obtained in 2017 for the April 7, and that the dashed line indicated the 68 percentile credible interval across the different method, and the solid line indicated the most likely value for the shadow diameter. Here we have we did also an analysis of a different using the calibration for a different model, and here we have KEHR GRMHT simulation, this one. Then we have dilaton. Here we have MHD dilaton metric. Here we have also an example of boson star analytic JP parameterization. Then we have like as I said, we use it also parameterized metric, and here we have another non-GR black hole metric, and also we did some analysis using like a wormhole solution. Just let me say that we didn't calibrate the boson star model. Is just to give you an example of what you see, if you have other model different from CARE. The summary is that in all case for which central brightness depression is present, the size, as you can see, the size of the ring light images scale with the boundary of the black hole shadow. Then now we try to answer the second question, if like Sagittarius star is not a black hole, but it's a compact object, and just suppose that as a surface that either absorb and thermally remit incident radiation or partially reflect, what happened, what we see, what we learn from this. We did a comparison of synthetic images of hot accretion flow around a black hole with corresponding images when the central object has a reflecting surface, and what we see here. Top left, we have a model images of Sagittarius star at 230 gigahertz, as seen by an observer that is at inclination angle of 60 degrees. What we have a relative diffuse elliptical feature corresponding to the equatorial emission from the accretion flow. We have a sharp circular lensing, and of course a dark region inside in the middle. The color scale corresponds to the brightness temperature, and top middle we have like a blurred images with a Gaussian beam, and top right you could see the reconstruction images of the first one with this imaging algorithm. Second row, we have what we did. We replaced this is a black hole. Then we replaced the black hole horizon by a reflecting surface with a certain radius and with an albedo. And what we see that we have like additional feature here, with respect to this one, and we have like thick bright secondary ring inside the shadow region. And again, we have a blurred version of these images. And here, again, we reconstructed with smiley. And what is our conclusion is that potentially detectable with EHT observation. So we have third row is similar to the second, but we changed the value of the albedo. And here we see that the surface is only marginally detectable. And the last one, again, we changed the albedo, and this is, as you can see, is indistinguishable, but from the first row. That the conclusion are for this second question is that using the observed image size and the broadband spectrum of Sagittarius star, we conclude that a thermal surface can be ruled out and a fully reflective one is unlikely.
Maria, how long do you have?
Yeah, just other two, I will be short. We used also this bound to place constraint on different metrics that are parametrically different from CARE, as well as like charged black hole and so on. And we what we have here, we have the constraint also using KEK and VLT. As we can see, VLT, the white part is the lowered part. We have we could say that we have an upper limit for VLT constraint and a lower limit for KEK. And okay, I will go fast. It's impossible to show you what all the tests that we did in our paper. Just I chose this one that I think that is relevant and is interesting. Then we compared this our result with the gravitational wave coalescing gravitational wave black hole, and what we will see that at the end, independent of the mass, the external space-time of all black holes are described by Kerr-metric. And what we take away and what we learn from this our analysis, that the images of such a star prove a unique and not explored region of parameter space of gravitational test. And contrary to the case of MT7, we do not have an ambiguity about the mass measurement, because mass was well measured by Keck gravity and also by the astrometric measurement. Then there are no wiggle room in testing the prediction of Kerr-metric. And just final comment, no? In spite of the fact that we have two different black holes with two different mass, different morphology, they are accreting in a different way. What we could conclude is that we are in agreement with GR prediction, and GR is scale invariant. That it's what was predicted.
Okay, thanks a lot for this talk. We are a little bit late, but I think still there should be room for one or two comments or questions. Okay, if not, everybody wants to have coffee, I think. Yeah. So I hand over to local organizing committee.
Thank you. Yeah, before you